Maze generation is a fairly popular topic in the field of algorithms because there are a lot of aspects to learn. Today let's take a slightly different look at this problem and explore dynamic mazes. First, let's settle the terminology and see the basics. A maze consists of cells that have 4 walls, each either on or off. The initial maze can be generated with any algorithm. The requirement is for the maze to be perfect. In other words, there needs to be only one path from a cell to any other cell, and there need to be no isolated or inaccessible areas. For simplicity, we'll call inaccessible areas lakes because they're locked. There are 2 approaches to generate dynamic mazes. If you inspect this perfect maze, you'll notice that adding or removing any wall will make it imperfect. So adding a wall requires removing another wall somewhere else, and vice versa. Notice that adding a wall in any place of a perfect maze splits it into exactly 2 lakes. So the problem simplifies into 2 actions. First, add a wall between any 2 cells that don't already have a wall between them, and delete any wall on the border of the 2 lakes, on the shore so to speak. It's possible to be done by going through the cells of either lake and collecting pairs of walls that are in different lakes. A wall can fully be described with a pair of cells. Another tip is that you don't need to collect the cells of both lakes, since there are only 2 lakes in total. If a cell isn't part of one lake, it is inevitably part of the other. The immense bonus of the algorithm is that the positions of the added and the removed walls are more likely to be far away from each other. This algorithm is likely useful for a game where the player is periodically blocked from going in a certain direction, in an escape scenario for instance. What if we needed to first delete a wall and then add one in the right place? One helpful thing to notice is that by walking from any wall of a perfect maze, it's possible to make it to the border of the field. If it's possible to get to the border of the field from any wall of a construction, we'll call it a peninsula, and otherwise we'll call it an island. The algorithm first picks a random cell that we'll call RC, and then those cells it has a wall with. It's possible that there are no such neighbors, so if that's the case, we do it all again until there is at least one. The algorithm is now 5 actions. Choose a random one from these neighbors, we'll call it Rn, make a path to it, remove the wall between RC and Rn, pick a random pair of consecutive cells from the path, and make a wall between them. As you can see, the island is connected to a peninsula. As always, I've made a demonstration where you can play around with the 2 algorithms and see the implementations.